All right, thanks for sticking around until this chunk of the video. Here we're going to prove that the expected number of flips until we see heads and tails is 4, and the expected number of flips until we see heads and heads is 6. And we're going to prove this using Markov chains. So Markov chains are a very useful model of probabilistic processes which obey certain rules. I'm not going to get too in the weeds as to what Markov chains are precisely. They are a very precisely defined mathematical gadget. And if you are interested in that level of rigor, you can look all over the internet. You'll find them all over the place, okay? Just Google search or DuckDuckGo search Markov chain. It's also going to be in most of your probability textbooks if you have one of those lying around. Rather than, getting really rigorous with it and giving you a full-fledged definition of this thing, let's just see it in action in this situation where we're interested in, and again, the expected number of flips until, well, let's start with heads and tails, okay? So we want to know the expected number of flips until heads and tails. So we're going to begin by setting up, again, this Markov chain for this coin flipping process until we hit heads, tails. Now, a Markov chain, very broadly, consists of a set of states which describe where we are in the process. And there are arrows which are called transition probabilities, which take us from one state to perhaps a different state, maybe even the same state. So what does this look like for this coin flipping process? So the first state, which I'm going to call stage 1, is where we are where we start out the process. We haven't flipped any coins. We're just we've done nothing, but we're beginning the process here. Now, what is a meaningful change in the state of this probabilistic process when we're going after a sequence like heads and tails? So here's the claim that I want to make. If you flip tails on that first flip, you really haven't made any progress towards heads and tails. In other words, it might as well be like you're still in the same state when you flip tails. Does this make sense? So when you flip tails, it's like you don't move anywhere. So 50%, and that happens, of course, 50% of the time. So what I'm going to do is draw an arrow from this state to itself, like this. And it's going to be labeled with the probability 1/2, or 50%. And maybe I'll even give a decoration to this to indicate that this is us flipping tails. Maybe I'll do that by writing in red here a triangle with a T in it. Okay? So that's us flipping tails. Now, when do we make progress in this process? We make progress and shift to a new state, which I'm going to call state 2, when we flip heads. So there is a transition probability that we leave this initial state and enter a new state in our system. And that happens again with probability 50%. So I'm going to put a 1/2 here, and I'm going to decorate this maybe in blue with an H. Not quite sure why I'm using triangles exactly. It just happened that way. This is not standard or anything. Okay, so one thing to notice, please, is that the sum of the arrows leaving state 1 is 1. This will always be the case with a Markov process. So let's say that we've flipped our heads. All right, we flipped the heads. Now remember that feeling that we felt when we discussed this flipping until heads tails thing in the last chunk of the video? We said that when we flipped heads for that first time, we got a little bit excited because we know 50% of the time we were free of this tedium. Whereas 50% of the time, of course, we fail. But the failure wasn't that bad because we still had a heads to work with when we failed after that first heads, right? So this is represented in the Markov chain in the following way. And see if this makes sense to you. We're going to draw an arrow which goes from state 2 to itself, represented by a probability, transition probability of 1/2. And that's when we flip another heads. This represents failure, sure, but the point is that it keeps us in this second state where we still have a 50% chance of winning, right? And that's exactly what this state sort of represents. We're going to have one more state, which is the winning state, which I'm going to call W. And this happens from state 2, 1/2 of the time. And of course, that's represented by when we flip tails. And again, I hope you see that the sum of the probabilities of the arrows leading out of 2 is equal to 1. All right. Okay. Now, we have one more state. And please notice that there are no arrows leaving this W. You can think of this like the process is done. But just to make this a Markov chain, what we're going to do is we're going to put an arrow which goes from W to itself, and we're going to assign it a probability of 1. All right? So what you should imagine is that once we get into W, we stay in W, right? We never ever leave W because we can't. Once we're in W in this process, we just keep looping around and around and around, staying in W. That's what's called an absorbing state in the vernacular, in the nomenclature, in the lingo of Markov chains and such. All right? So we stay in W. All right. Let's contrast this Markov chain, shall we, with the Markov chain for the HH process. Because it's different, and it's importantly different. So we still have the same starting state, which I'll call 1. All right? And it's still the case that if we flip tails, we will not make any progress toward our goal of flipping H then H. So here, we still have this 1/2 probability of flipping tails and making no progress. So look at the resemblance here. And it is also still the case that we have 1/2 probability of making progress and entering into a new state, a distinctly new state in our model, in our process. This happens when we flip heads, and that happens 1/2 of the time. And again, this is when we flip heads. Okay, cool. Now, here's the key difference between the models. From this state, we can either flip heads or we can flip tails. Of course. But whereas in the previous state, when we flipped heads, and remember, that represented failure to win. If we fail to win now, and what does that look like? That looks like flipping tails. Please note that we don't stay in state 2. We go back to state 1. This is that idea that we are going back to square 1. I guess in this case, we would be going back to circle 1, state 1. And that happens 1/2 of the time. And the other half of the time, well, that's when we win. So let's denote this. Let's put this into our model. So we win 1/2 of the time. What happened when we did that? We flipped heads. And the other half of the time, well, we failed. We flipped tails. But the key thing is, that doesn't keep us in state 2 like failure over here does. It takes us back to state 1. So this happens half the time again. And that is represented by us flipping tails. And finally, to make this an honest to goodness Markov chain, we're going to have a transition probability of W to itself of 1. So that, again, once we get into W, we cannot escape W. And furthermore, this is what's called an absorbing state for this Markov chain. So these Markov chains are sort of a graphical representation of this intuition that I was giving you that you could give to your enumerate uncle, or at least try to give to your enumerate uncle. Okay? And now what we are going to do is use these Markov chains to compute the expected value of the number of flips until we enter the winning state of each of these Markov chains. So now, when we talk about the expected number of flips, we're imagining flipping a coin. Every time we flip a coin, we are taking a step in this Markov chain. So really what we're going to be computing with these Markov chains is the expected number of steps, the expected number of transitions that we are going to make until we enter this absorbing state W. Similarly over here as well. We're going to compute the expected number of steps. That's what they're called. They're called steps of traversing this Markov chain with these probabilities, with these transition probabilities. The expected number of steps until we hit W. This is extremely easy to do, to compute these expected number of steps. All you need to know is basic solutions, so knowing how to solve, rather, linear systems of equations. Okay, so we're going to do that next. All right, one last piece of the puzzle here. We're going to now compute the expected number of steps or expected number of flips until we reach this absorbing state W. And this is a remarkably simple calculation. Let's call the expected number of steps till we hit W starting at 1. Let's call that E sub 1. So E sub 1 is going to be the expected number of steps until we hit state W starting from state 1. All right. And we're going to call E sub 2 the expected number of steps until we hit W again, starting, but instead of from state 1, of course, we're going to start from state 2. All right. And just for completeness sake, we're also going to define E sub W to be the expected number of steps until we hit W, starting, and this is a little silly, from W. All right. Because we can see right off the bat what EW is. We don't even have to think. EW is 0, right? So in fact, we know that. EW is 0. So maybe let's do some calculations down here. We can start off by our realization. EW is 0. Because if you start in W, you don't need to take any steps to be in W, right? We've hit it with 0 steps. So EW is 0. Now, what's E1? Well, E1, after all, is what we're looking for. So it would be a little bit rash of us to just sort of say what number it is. The point is that using this Markov chain picture here, we can write down an equation for E1 in terms of perhaps E1, E2, and EW. to see what I mean, let's just take a look. So E1, the expected number of steps to get into W from 1. Well, certainly we're going to need to have at least one step. And so I'm going to write a 1 plus here. All right. That 1 representing the one step that we need to leave state 1. Now, 50% of the time, we stay in state 1, right? And when that happens, 50% of the time, well, what we're going to add to this is 1/2 of the expected number of expected number of steps to get from 1 to W, because 50% of the time we stay in this state 1. And so the number of steps that it takes to get to W, of course, does not change just because we were in state 1 and then re-entered it. I hope that makes sense. So one portion of the term for this equation, we're not done yet, is that the expected number of states to get from state 1 to state W is going to be, well, the 1, again, that's the step that we take in leaving this state. Here, we're going to represent the chance that we land back in state 1 by 1/2 E1. And the chance that we land in state 2, well, that's going to be represented by the fact that 1/2 the time we're going to land in state 2. So the additional number of steps to get into W is going to be represented by 1/2 the expected number of steps to get into W starting from state 2. So hopefully this equation here makes sense. And finally, let's write an equation for E2, which is very similar. E2 is equal to 1 plus, let's see. Well, so half the time we stay in state 2. So that's 1/2 E2 plus 1/2 EW. Great. So now what we have, I want you to observe, is a system of 3 equations in 3 variables. EW, E1, and E2. And you probably have learned at some point in your life how to solve these things. So let's just go ahead and do that. It's remarkably simple here. So for example, we can take this equation here, E2 equaling this garbage here. First of all, we can realize that because EW is equal to 0, this term right here is 0. So we can just sort of kill it, dead. Then we can subtract E2 from both sides, or excuse me, 1/2 E2 from both sides, to obtain that 1/2 E2 is equal to 1. And this, of course, implies that E2 is equal to 2. Which is a nice fact to know, but it's not what we're interested in. It's not what we're interested in. Remember what we're aiming for. We start in state 1. So we would like to know the expected number of steps in this Markov chain to get into W starting from 1. In other words, we want E1. Easy to obtain now because we can take this E2 value, we can shove it into this equation, and what we obtain is that E1 is equal to 1 plus 1/2 E1 plus, now 2 times 1/2, that's 1, right? So that's great. Oh, Peanut. Okay. Sorry, my dog is being weird. Hold on, wait. Peanut, go on outside. Little interruption there, sorry. So then we can subtract E1 from both sides, 1/2 E1 again, and get 1/2 E1 is equal to 2 in this case. So guess what? E1 is equal to 4. Looky there. E1 is equal to 4. Great. Hey, and didn't we say, isn't that what the computer said was going on? Remember way back in this video, we saw that the average number of flips until we saw heads, tails was 4. Empirically, we found that. Okay, great. So the mathematics and the empirical observation agree. Let's play the same game here. This is a fun game, okay? Let's play the same game here. Again, EW is, all the same definitions hold for this Markov chain as well. EW, still 0, right? If we're in W, how many steps does it take to stay in W, or to hit W? 0, because we're in W. What about E1 now? Well, E1 is going to be the one step represented here, plus half the time we end up back in state 1, and half the time we end up in state 2. Note, these two equations for each of these two models are the same. What's going to be different, of course, is the equation for E2. And what will E2 be? Well, half the time we end up back in E1. So we're going to have the one step for leaving state 2, but half the time we're going to end up back in E1, and the other half of the time we're going to end up in state W, where we want to be. So look at the key difference here. The key difference in this equation here. I mean, again, this is going to die in exactly the same, for exactly the same reasons as we saw previously. EW 0, hence that term there is 0. But now look at this, the difference here in these equations. This difference is what accounts for the different values that we're going to see in the value for E1. So, in fact, this is even more straightforward. We can just substitute this expression for E2 into this equation. And if we do that, we learn that E1 is equal to 1 plus 1/2 E1 plus 1/2 times, now what I'm going to do is substitute this E2 right here by 1 plus 1/2 E1. So let's just work through the details here. This is 1/2 E1 plus 1/2. I'm distributing now the 1/2. 1/4 E1. So 1/2 E1 and 1/4 E1, that sounds like 3/4 E1 to me. This 1 plus 1/2 sounds like 3/2 to me. We can subtract 3/4 E1 from both sides. Then we can multiply both sides by 4. And then we can reduce this dumb fraction into 6. You see the discrepancy? And you see the agreement with our empirical observations that we did using the computer, right? So E1's 4 for HT. The expected number of flips until HT is 4. The expected number of flips until HH is 6. Well, that's that. I hope that you all enjoyed that explanation. I find this stuff to be just sort of a lot of fun, that you can take a probabilistic process like coin flipping and see such different values, and maybe not so intuitive, right? But now, not only do you have a nice, concise explanation for why there is this difference, which is reflected in these Markov chains, but now you know how to compute on the nose exactly what the expected number of flips is in each of these cases. All right? All right. Till next time. Bye.